Hello everyone, my name is Mazan Ashraf and I'm here today to talk with you about transitive closure and how Warshall solved it. Let's start by defining what is transitive closure. Transitive closure is a graph that refers to the identification and inclusion of all possible indirect relationship between nodes based on the direct relationship we already present in our graph. What is the importance of transitive closure? It's important that it helps us in social network where transitive closure help identify indirect connection between individuals. Also, it helps us logistically to determine all possible routes between locations for efficient transportation planning. We have a graph example right here. So let's start by finding the transitive closure for it. Let's start from node 3. From node 3, we have direct connection between us and node 4, and also from node 4 there's direct connection between node 4 and node 1. So therefore there's going to be indirect connection between node 3 and node 1. And from node 1 there's direct connection to node 2. Therefore there's going to be indirect connection from node 3 to node 1. If we start from 4, we have indirect connection from node 4 to node 1 because we can go from node 4 to node 1 and from node 1 to node 2. So here is the solved example as we just discussed. Now let's start by talking how Warshall solved this problem with his algorithm. First of all, Warshall used the adjacency matrix. He started by selecting iteratively each row and each column. So first of all, he selected the first row, and also selected the first column. First column and first row, and he had now sub matrix. This sub matrix, he's going to iterate over each one of its element and decide if he's going to keep the element the cell as it is or change its value. If the cell is 1, he's going to keep it as it is. If it's 0, we have two options. First of all, we can change it to 1 if in the selected row and selected column values, the respective values is 1. Or if it's a 0, we keep the value in our cell 0. Let's start by giving an example. In this cell we have a 0. Okay, so we're going to check. In the selected row we have 1, but in the selected column we have 0, so it's going to stay as 0. But in this cell, the selected row is 1 and the selected column is 1, so it's going to be changed to 1. So we have and the rest is going to stay 0. And the code and the algorithm iterates over each row and each column. Here's an example of how we changed it. If there is a selected row and selected column 1, so we're going to change the value to 1. And here the pseudocode for the algorithm, he used this for loop to iterate over each selection for each row and column, and he used these two for loop to decide which cell he's currently standing on. And he checks if the current cell is standing on is 1, so this element this is going to put 1 in it. Here is an OR condition and so if here is a 0 and here is 1. So it's going to keep it to put 1 here because 1 or 0 is going to be 0. But if this is a 0, so we're going to check in this element. If we have in the selected column and in the selected row, if the element is 1, so the ending for them is going to be 1. So 1 and 0 is going to be 1. But if nothing is achieved, so it's going to be 0 or 0. So the value we try to keep is 0. This is the pseudocode. Now let's go over our code, our implemented code in Python. Here is code. As you can see right here, we receive as an input the edges, not an adjacency matrix. So we built our adjacency matrix ourselves. Here we start by putting 0 in each element, and then we iterate over the matrix and check if the edge is the same as the row and column. We put 1. Now here is the algorithm that Warshall used to solve this problem. This is the for loop he's going to use as iterate over which row and which column he's going to select, and here is the iterate for over each element in the matrix, and we check if the matrix of R and C is 0. So we're going to check if the matrix of the selected element of the selected row and the current column is 1, and if the matrix of the current row and the selected column is 1, so we're going to put in the matrix 1. Else we're not going to change anything. And here is our starting example. We started by 2 and 1, 2 and 3, 3 and 1, 3 and 4, 4 and 1, 4 and 3. And in the above code, we are going to have explanation for each step and what we did in this step. As in right here is the output for the above algorithm. We started by filling the matrix with zeros and then building our adjacency matrix. And now we started in the code for Warshall. He selected the row 1 and column 1, and he started by iterating over each cell in the matrix. And we have a bonus examination after each trial, after each selection. He gave us our adjacency matrix update. So we started by this, and after our first update is going to be this. After second update is going to be this. After third update is going to be this, and finally is going to be this after fourth update. And we also provide the new edges we provided. We started by 2 and 1, 2 and 3, but we added 2 and 4. We started by 3 and 1 and 3 and 4. We added 3 and 3. We started by 4 and 1, 4 and 3. We added 4 and 4. Now let's start by calculating the time complexity. Here in our code, the time complexity is 3 for loops, and our base function, base function is right here. So it's going to be 1. So 3 for loops and of 1 is 3 summation of 1. Let's start by analyzing the last summation and ignore the rest. The last summation is summation of 1, so the rule is going to be upper minus lower plus 1. So v minus 1 plus 1 is going to be v. Substitute the value of the first summation in the rest of the problem, and select the last and ignore the rest. So it's going to be summation of a constant. So the rule is going to be constant of upper minus lower plus 1. So it's going to be v multiply v minus 1 plus v. So it's going to be v multiply v is going to be v squared. Substitute and solve it. It's going to be the same rule, constant of upper minus lower plus 1. Finally, we are going to end up with v cube. So therefore, our time complexity for the algorithm of Warshall is going to be peak O of